Hi, welcome everybody. My name's Steve Wally, and I'm the governing board chair of the Confidential Computing Consortium. The consortium was formed back in September 2019, and it's a non-profit organization under the Linux Foundation umbrella. We focus on open source licensed projects, securing data in use, and accelerating the adoption of confidential computing through open collaboration. Our members are a broad collection of cloud service providers, chip manufacturers, and independent software companies. Enarx is one of the first projects that joined the consortium right at the beginning, and I'd like to introduce you to Mike Purcell and Nathaniel Mccauley, two of the founders and maintainers of the project, to tell you more about the project and give you a deep dive. Mike?
Thanks, Steve. Good to be here. Yeah, I'm Mike Purcell. I'm part of the Office of the CTO at Red Hat. I'm one of the co-founders of the Enarx project, and I'm joined by
Nathaniel McCollum, and I'm a senior principal engineer at Red Hat, where I'm also one of the co-founders of the Enarx project.
Excellent. Well, without further ado, let's get on. So I thought I'd skip to the most interesting part, which is the state of the project. You know, where are we and what we're doing? We'll come back to this, but the answer is that we have an end-to-end demo available, and we will be showing you this on SEV. Now, we have imminently SGX demo on Intel, but sadly not quite ready for you today. But so close. If it weren't for X509 certificates, we'll be there. We hope to have a standalone proof of concept framework available soon, i.e. you can start playing with it. There'll be some restrictions, but enough for you to compile and use it. So we really want you to do that. And of course, after that, we really ought to write a bit of documentation. There is some, but frankly, not enough. We know that. We've been pushing very hard to get this demo out to you, and we need to put some focus on that. So that's where we are. You'll soon find out exactly what that means as we go through. But that's the state of the project. So let's start with a bit of an overview of Enarx itself. What we plan to do, by the way, in this is for you to get questions. If you have questions, please enter them into the Q&A, and we'll look at them. And if you have questions about a particular section, maybe put down the slide number associated with that, if that would help. And on the whole, we'll answer them at the end. We hope to leave lots of time for questions. If there's anything sort of clarifying questions, then we may stop and answer that. But on the whole, we're going to at the end. But we really want lots of questions, so please put them in. Okay, so a bit about Enarx. So the very brief 5-bullet overview. Enarx is about using trusted execution environments for confidential workloads. And you'll see we say confidential for TEEs, not just one. We are a cross-platform project. Really key for us is it shouldn't just be easy to develop. It should be really easy to deploy. And we'll come in a moment to some of the reasons that's not always the case and why hopefully Enarx helps you with that. But if people are going to be using TEEs, we want to make it easy. But we don't want to be compromising on principles in terms of security. It's so easy to get security wrong in so many ways. We want to try and make it difficult to do the wrong thing. That's the key thing from our point of view. And you know, we absolutely see this as a cloud native play. You know, we'd like to be integrating with OpenShift, Kubernetes, but also there's some really interesting things going on the edge, which I suspect we'll come to a bit as we go through. Last thing is, we're an open source project. We are not production ready yet. You know, we hope to get there one day. But this is a project, not a product. But the way to get it to be a product is for you folks to play with it and to start getting it there. All right. So let's first talk a bit about why we need this. So when we talk about isolation of workloads, there's actually three types of isolation that we can talk about. Let's say you're a tenant of a cloud, and on the left-hand side you have a cloud host, and there's at the bottom there's an OS, a hypervisor, and stuff like that, and then you have your workload or running on that, and that could be a VM, it could be a container, it could be bare metal, but you may not be the only tenant with a workload. So there's a gray one there as well. So there's three types of isolation. The first type is workload from workload isolation, i.e. you do not want another workload, particularly from another tenant, to be able to interfere with your workload, whether that's stopping its operation or looking inside it or making changes. So you want integrity and confidentiality protection in particular. And in fact, the state of the art is quite good for that. We know how to do that. Containers and hypervisors and even process are quite good at that. This is pretty much solved to most degrees, I'd say. The second type is host from workload isolation, and this is to say, if I'm running the host, if I'm the cloud service provider, I really don't want a workload malicious or compromised to be reaching down into the operating system and making changes there, because that messes up me, it messes up other tenants. And again, this is something that actually over the last 5-10 years we've got pretty good at as an industry. Hypervisors are good at this. Containers are pretty good at it. SE Linux, those sorts of things, and provide us with some pretty good protections. The difficult one is workload from host isolation, because the way that standard classical virtualization, whether containers or VMs or just standard computing, it works is that if you have privileged access to the host, whether malicious or compromised, you can see inside workloads. It's as simple as that. You can see inside and you can mess around with them. And how to deal with this is what the Confidential Computing Consortium is about to a large degree. It's really important in lots of cases. There's lots of sensitive workloads that you might be running, whether it's your payroll, maybe credit card, health information, or cryptographic keys. And across many sectors, particularly highly regulated ones, and particularly on vulnerable hosts. But that's not just cloud; it can be edge and IoT. So I'm going to carry on here because I want to get into the technical stuff about how we do this, because TEs are how we do this, right? And they sound great, but they come with some problems. First one is that there are different platforms. The best known ones at the moment are SGX from Intel and SEV from AMD, but there's two more that's been announced already: PEF from IBM Power and TDX from Intel. And you don't want to have to do separate development for each. That's painful. Nathaniel, I'm going to hand over to you. Let you do the rest of this slide. You've got some good talking points on this slide.
Sure, thanks, Mike. One of the important things that that we wanted to make sure that we captured in Enarx was the ability to use whatever language you wanted. And with the existing solutions that we have primarily in the space, there's lots of different SDKs, but most of these are focused on languages like C and C++. And so trying to use those other languages to build on top of these SDKs can be a bit restrictive. Let's go to the next one. So they also have different attestation models, and this is really a tough thing to work around. So the way that you, for example, attest cryptographically a working system for SEV is dramatically different from the way that you attest a working system using SGX. And this is true for basically all of the technologies. So if this becomes an application level concern, then every application has to be able to handle all these platforms that it works on. And the decisions themselves that have to be made as part of attestation are very complex decisions. And one small error can result in pretty catastrophic results. So we definitely want to be able to share that code. We want to make it centrally audited, and that's a major concern.
Yeah, we should just quickly explain for those of you who aren't aware. Attestation is the mechanism by which you check that the thing you're running is what you think you're running. And there's lots of cryptography in there and lots of complex stuff going on. And we'll talk about some of that a bit later on. Next point.
Yeah, so then another point is that we have different vendors. So if you are built on top of one particular vendor, for example, and there's a vulnerability discovered, as there basically have in all implementations, and if you have this vulnerability, what is your mitigation strategy for this? Just having implemented on one solution means that you're pretty stuck. And if you're regulated, that may mean that you basically have to shut down your services. And so that's a pretty high cost to pay, and we need to figure out a solution for that. And really fundamentally, you just want to deploy workloads, right? You have a workload, you want to deploy it. and you want all of these problems to be solved for you. So this is precisely what we hope to do with the Enarx project.
So introducing Enarx. So we have a runtime, and the runtime is what you run your application on, whatever platform you're running in. Nathaniel, why don't you go through some of the different pieces of this and some of the differences?
The first thing that we do on the bottom is we want to abstract away different types of TE technologies. So currently in the industry, we have two different types of technologies. On the left-hand side, we have process-based ones. These are things like Intel's SGX and RISC-V's Sanctum. On the right-hand side, we have VM-based technologies like AMD's SEV, Power's PEF, and Intel's TDX. And we want to provide a single interface to be able to work on those. So the first thing we have to build on the bottom is essentially our hardware abstraction layer to be able to run workloads appropriately across both of those technologies. The next level up is WebAssembly. And this is the interface that we want to expose to applications precisely because it's a standardized interface. So WebAssembly and WASI are the two principles here. WebAssembly is currently standardized and is ongoing active development and revision in W3C. It's growing rapidly, and languages are very quickly adopting support for a compilation target of WebAssembly. WASI is a little bit newer and is currently undergoing stabilization. WASI is the basically your system interface for WASI or for WebAssembly. You can think of this sort of like Syscalls. So, you know, if you're going to read or write to a socket, or if you want to get some random data, like all these kinds of syscalls are syscalls that are standardized in WASI. So this founds the bedrock of what we are actually exposing to interfaces, and this is standardized. So you don't write your application to Enarx, you write it to these open standards, and then you can just deploy with Enarx. On top of this, you get language-specific bindings. So, for example, if you're writing in C, you get a libc implementation that uses WebAssembly and WASI. And then your application should hopefully work fairly unmodified on top of that. Mike, you have a question?
I'd go even further and say you're not writing to WebAssembly or WASI. You're just writing in your standard language, and the compilation is targeted at WASI. So you shouldn't need to think about it. This is one that we talked about, you know, having to write in particular languages. This is what we want to avoid. We want you to be able to write in any of the languages that WASI that support WASI, and there's lots of them already: C, C++, Java, Go, Rust, .NET, a whole bunch of them. So that's what we want to make easy for you to use. We want to put this into the your CI/CD pipeline and make it easy. So let's just have a quick architectural view of how all the bits fit together. So this is kind of a bit of a redo of the picture we showed before. We have the client on the right and the host on the left. So on the left-hand side, we have the TEE, and that the TEE sits in is in the big white box with the green stuff in it. Everything in the green is trusted by the client. In the Enarx model, we care about the client more than we care about anybody else. We want the client to be able to trust what they're doing and that it should execute with really high levels of assurance. So we are going to be setting up a keep, which is a TE instance, and we put the runtime and application, which is what we just saw on the last picture, those 5 or 6 layers. That is what you're seeing here on the left. Now on the right, we've got the client, and we have an Enarx client agent, and that is going to work with an untrusted piece on the left, which is an Enarx host agent, to set up your keep. Now, the key thing here, and we'll talk about trust relationships in a bit, but in the Enarx model, you do not trust the host at all, apart from the CPU and firmware. And you need the CPU and firmware because, well, something's actually going to execute instructions. So in the Enarx model, you trust 3 things and 3 things only. You trust the CPU and firmware. You have to trust those. You trust the application that you've written, and well, you'd hope you trust that, and you trust the Enarx runtime and the Enarx or the pieces of Enarx. So we'll talk about how that relates to open source in a bit, but those are the things you trust. I know you don't like this picture very much, Nathaniel, but I put it anyway because it just goes into a bit more detail. We won't. You can talk to a bit if you want, but it's there just for maybe refer to it later on if people have questions. Do you want to add anything to this? You're muted.
There's a variety of different parts here. The important bit is that the client agent is responsible for actually deploying the workload. So it takes in a WebAssembly binary that could be, a standalone file in your file system that you've just compiled, or it could come from a WebAssembly repository somewhere that you want to deploy from. And the Enarx client job is to take that image and to get it to the host in a secure and confidential way, along with any other data, configuration, keys, all of that kind of stuff. And it delivers all of that into the keep on the left-hand side on the host side without the host being aware of what's actually happening. So the host does not have visibility to either code or data that happens that's running on the host.
Yeah, we've got some slides in a bit which talk about give the process a view of how that happens.
We'll go through that. But basically, one thing to point out here is the shims. So each different type of technology has a separate shim. So, for example, there's an SGX shim and there's an SEV shim, for example. Each one of those adapts the specific technology to be able to run the code on top of it, and that's how we get our hardware abstraction. Other than that, all the WebAssembly and a tester and app loader and application, all that stuff is shared on the top across the different technologies.
Excellent. I think we should show a demo. Right, let's do that. I just need to go to a different window and we'll start this. So, okay. What we're going to do is we're going to get a Rust application, and we're going to download it, which we've just done, and we're going to look at it, and then we're going to compile it to WASM. We said that would be easy. So this is a very simple application. It gets a random number, it formats it up, and then waits 20 seconds before displaying the answer. That's all it does. It's pretty simple. And we're going to build it, and we're going to build it with a target for WASM WASI. And it's really that simple. This is a real-time demo. I mean, I'm not doing it right now. It's recorded, but this is a real-time demo. Give or take a few seconds. So what do we need to do? We need to deploy the WebAssembly. So we use the Enarx command with the command deploy, and then we just give it the path to the thing we want to deploy. There we go. And then we say, well, we need to deploy it to a host. What is the address of the host? That's the address of the host. And it should be listening on this port. Okay, so we're now on that machine, actually. And there we go. And we've started the server. And yep, it's started. It's good to go. So we now need to deploy it. Now, before we do that, we are just going to show the output using Journal Cuttle because we want to be able to see what's going on. And we've got something down the right, which it's quite a nasty thing. We'll show in a minute. So we're now deploying that workload. And oh, look, it started. This is great. Okay. Now, this thing down here on the right is going to search in fact, I'll just stop it for a moment. What it did is it searched the process space of the memory associated with that process to see if it could find the secret, which is still hidden. I mean, I've just paused it. It'll be a bit more than 20 seconds. Still hidden, and the answer is it did. This is a terrible, terrible thing, surely, because we don't want that to happen. Well, the reason it happened was because actually we deployed this WebAssembly as just straight WebAssembly and not in a keep. And there it is. It found the thing. So if we're just running bare metal, this is what happens. So what we'll do now is we will edit the client configuration, say, okay, we're not going to just allow deployments like that. That's far too dangerous. We're going to deploy into a standard VM and hope that the VM will do a better job for us. So we've deployed that. It's waiting 20 seconds. Let's see if the VM gives us any better protection from this malicious and really nasty little program down the bottom. Let's maybe we're safe with a nice KVM VM. And you can see on the top right, it's got, oh dear, we're not safe. So this should come as no surprise. KVMs and VMs don't help you in this case. So the last thing we're going to show you here is we're going to deploy to SEV. So this is a proper SEV keep, fully attested. We've made full cryptographic checks. And so creating there we go. And if you look on the left, it does say that keep attestation verification succeeded. And we've created the keep on the right, and we're going to search again. So our hope is that because it's in a keep, it is protected. Its confidentiality is protected from the rest of the host. And indeed, that's exactly what we've seen. It was unable to read the secret. There was a secret created, but we were unable to see it. So let's go back to the slides, and we'll show you what you've just seen. What you've seen is basically this. In step one, we used the CLI to talk to the Enarx client agent. And the client agent spoke via the Enarx host agent, which is the server. And it worked with the CPU and firmware to create a basic keep. And once that had happened, the measurement of that went back to the Enarx client agent. And it checked that measurement to check that it was correct. And only when it had done that, it then took the WebAssembly file and encrypted it under a session key, which is unique to that keep. So if we had created another keep on the same machine, it would have been a different key. It encrypted it, sent it to the keep where it was unencrypted, because the keep has that key, and then run as a standard WebAssembly application. So we asked for a keep, we did an attestation, verified the attestation, encrypted the workload, sent the workload, and ran it. That's what we've just seen. And for those of you who prefer this type of view, there's this. We'll make these slides available and the video of the demo if people want to look at it in more detail. And there will be a recording of this shown as well. Nathaniel, anything you want to add at this point?
I think you've covered it well. Thanks.
Okay. Okay, well, you can talk to the design principles then.
Yeah, so one important aspect of any project that's working in this space is that you have to have some very strong design principles. And these are things that essentially you are not willing to compromise for expediency. So you want to be able to have high standards, and we believe that we have adequately captured these high standards. So let's go through them briefly. The first one is a minimal trusted computing base. So one of the key points here is that because you are establishing you're extending your trust over to a hostile party, you do want to make sure that the bit of code that you trust is incredibly small. And so Enarx works very hard to make sure that everything that's in there is very small. Currently, our entire runtime, that's everything you need to make your application running, is about 5 megabytes. Just deploying Grub and Linux, for example, in a virtual machine is substantially larger than that. So we have a very small trusted computing base. The number two is the minimal number of trust relationships. So we don't want you having to trust lots of third parties. We want to keep that down to as few as possible. And that's basically just the CPU with the firmware that you're running on. That's Enarx, and that's whatever code that you are trusting. So number three, deployment time portability. This is something that's really important to us because, as we mentioned before, if you have a vulnerability, you need to be able to redeploy your workload immediately to another platform. And Enarx allows you to do that by having deployment time portability. So you can take that same exact WebAssembly binary, you can move it over to a different CPU, and you can be running within seconds. And
let me talk. I think that's a really important point. In the demo we saw, you saw me using Emacs, the king of editors, to edit that configuration file. You may have noticed that SGX was another option there. If we put SGX there and it were running, we would be deploying exactly the same WebAssembly binary. No changes at all. We're not recompiling. We're taking the same compiled code and just running it. For us, that's really, really important basis for what we're doing. Sorry, do carry on, Nathaniel.
Thanks, Mike. So number 4 is that we want to have a network stack that's outside of the trusted computing base. And this is important because this solves a whole class of issues by simply having the parsing of network packets largely be happening outside of the trusted computing base. There's been a number of vulnerabilities in the Linux kernel in this regard, so the history is not really great, and we want to just solve this whole class of problems ahead of time. So number 5, we want to ensure that we have security at rest, in transit, and in use. And so although we're not fully there yet, it's our intention to basically have any persistent storage is automatically encrypted on the host side, and any network traffic is enforced to be encrypted so that you don't get naked sockets coming outside of the keep. And this makes sure that you have vertical integration all around the security, and there's no place to basically make mistakes. You can hopefully rely upon the default configuration. Number 6 is auditability. So everything we do is aimed to be auditable. When we write our code, we always choose code style that aims to be easier to audit. We keep our functions small. We keep our files small. We hopefully write self-describing code, and we document things that are not as clear. So we hope to have strong principles of auditability. Number 7, everything we do is open source. This should be no surprise. This also goes towards auditability and trust, but you can take what we've built, and you get all the freedoms that comes with open source software. So number 8 is a strong emphasis on open standards. We don't want you to have to build something on Enarx. We want you to be able to build things using open standards and to be able to deploy them with Enarx. So we emphasize the use of open standards there. Number 9 is memory safety. We care a lot about memory safety because whenever you have memory that's not safe inside of a keep, you have very drastic repercussions. And so we lean heavily on WebAssembly, which is pretty good in this area, as well as Rust, which provides a memory model that has very strong safety guarantees. And we are very careful not to use unsafe code as much as possible. So that's memory safety. And number 10 is a commitment to no backdoors. All of our developers have made commitments that we will not be involved with putting any backdoors in Enarx, and you can trust it for your workloads.
And
Mike?
That's, again, one of the reasons that we believe that open source is important. So auditability and open source allow you to have assurances around the lack of backdoors. That's really important. Okay, so just a bit about why this is an open project. Well, first of all, the things we've just talked about, right? About auditability and making sure, but we want to, there's broader reasons. First of all, there's diversity of thought and experience. The more people with different viewpoints who are involved, the more use cases we'll have. For instance, we had some people being involved who have some embedded systems knowledge and some edge interests, which have made us look at things in slightly different ways. More people, again, can explore the architecture, challenge designs. We have a very friendly but quite rigorous mechanism just in the culture of how we run the project for challenging designs, and then reviewing implementation, increasing test coverage, and of course clarifying documentation, because without documentation you can't be sure what you should be doing in the first place. So we value that, and that's another reason for openness. The other thing, of course, is ease of involvement. We absolutely want more voices and more expertise, and that requires a welcoming environment. If we make it difficult for people to feel welcome, then we're not going to get that diversity that we need. And we want that auditability, but we can only really do that if we combine it with the other two things. So this is, part of the reason we're open source, and part of the reason we're part of the Confidential Computing Consortium, because that involvement allows us to pull on a broader pool of expertise and interest and knowledge. And hopefully, with this webinar and further discussions and community involvement, we'll be talking at FOSDEM and RSA and places like that. More people such as yourself can come and get involved. Nathaniel, do you want to talk about this one?
Sure. We are an open project. Hopefully that's been made explicitly clear. All of our code is available on GitHub. All of our wiki is available on GitHub. All of our design is available on GitHub. Our issues and PRs also on GitHub. No surprise there. Everything that we do is open, including all of our chat, which is available on Rocket Chat. Thanks here to Rocket Chat for sponsoring our chat server. All of our CI/CD resources are open and available as well. So a huge thank you to Equinix Metal for the donation for this. One of the important things that this means is that if you are interested in contributing to the project and you need access to the hardware, access to the hardware is definitely something we can provide to you. So don't, if you're interested in contributing, please don't let that stand in your way. So we have status meetings, which are open to all. So basically all of our meetings happen in the public. You're welcome to come along, and we would love to hear from you. In terms of diversity, we've committed to the Contributor Covenant Code of Conduct, which is pretty much the standard these days. So in every ways, we are open and we are looking for your involvement. Please come join us.
Yeah, so let's just recap briefly on the state of the project. Hopefully it makes a bit more sense now. So that end-to-end demo, you've just seen it. That proof of concept for actually creating yourself, we hope to have it available early next month. Too much of it is currently sitting in a private repo, which is my bad, but we'll get it out. And then, of course, the documentation to make it easier to do that and to understand how we can move forward and what the next steps are. Where are we in terms of the project? If you look at the next slide, you'll see that some of these are grayed out. So we have working proof of concept for all parts of these, apart from the grayed out pieces. Some of them are very important, and some of them we've basically skipped for now. For instance, OpenShift Kubernetes integration we haven't gone on with yet. We are doing attestation measurement, but we're not doing it in the way we intend to do it in the long term. And our way of doing keep runtime repositories is very simple at the moment, for instance. But you know, so that the absolute majority of the pieces are there. They are running, and they are there to be played with and coded. So, Nathaniel, do you want to talk about what the different pieces are?
Sure. We'll just go over, we actually have many different repositories in our GitHub organization. Many of these are dependencies we've had to build for various utilities and such, but we'll talk through the main ones that are important. So the most important, the center of our universe, so to speak, at least today, is the Enarx keep loader. This is the binary which actually does the setup of the keeps and facilitates communication in and out, facilitates syscalls and so forth. So if if you were comparing this to a container, keep loader would be effectively your Docker run. WASM loader is our second crucial binary, and this forms the basis of everything above the hardware abstraction layer and up. So this is compiled to a static ELF binary and is executed inside of the keep loader. This is what does all the communications from the keep inside to the tenant, and it is what deploys and executes the WASM code as well as setting up the configuration environment. One thing to note here is that this is a fairly modular approach. So keep loader can load native binaries. If WASM loader is not your thing, you can write your own. However, we are providing tight integration between those two pieces. So there would be a lot of things you'd have to build yourself, including attestation. So we recommend using the WASM loader. On our next repo is called Keep Manager, and the job of Keep Manager is to manage the life cycle of keep loader instances. So when a client connects to the Keep Manager, it says, please give me a keep. The Keep Manager will set up the keep loader and facilitate communications that are untrusted before the client switches to direct communication to the keep loader. The Keep Manager's job is to just basically supervise the keep loaders throughout their lifetime on that local host. then of course, on the tenant side, we have our client, and this repo name is going to change. We haven't figured out exactly what we're going to do with it yet, but our client today basically takes that WebAssembly binary, it talks to the keep manager first, sets up a keep loader instance, and then pivots to speaking directly to the keep loader over a secure channel that's secure and attested, and from there it can actually deliver its code. We have many infrastructure and glue repos. We try to follow best Rust practice of keeping our dependencies small and self-contained, self-documenting, as well as having extensive documentation. So hopefully we've done that well. We have, for example, some platform-specific things. So we have an SEV crate and an SGX crate, for example, which form the basis of the hardware structures and instructions, a little bit of assembly and so forth to make sure that that these things work. We have a utility called Sibor, which we are actually hoping to ship very soon as a first release. And the purpose of Sibor is to manage all of the hardware on an AMD SEV host. It's a general purpose tool, and we are actually in conversations about making this able to actually measure and deploy like QE move VMs, for example. So please take a look at that. We have a library called Koine, which is basically shared code between our client and the keep manager and keep loader. So that's all of our network data formats, for example, are there. We also have an implementation called Siborium. So if you're interested in doing Sibor, that's what Siborium is for. It's a Sibor encoding and decoding crate. And we had to build this because although there was another crate, it is no longer maintained and has some significant issues. So we have created a new one, and hopefully it will provide a much better experience. So we have a lot of code currently getting merged. Like Mike said, what we showed in the demo is currently not committed yet, but we are working to commit it in the coming days. So I think that's a pretty good overview, Mike. Did I miss anything?
That's great. Thank you. No, you got to the point about my not having merged everything. We will get there. So how can you get involved? Well, first follow us on social media. We'll give you some details, and you'll find out when new stuff happens. We're now, or very soon, at the point where you'll be able to download, compile, run, test, report, and let us know what works and what doesn't. I say download in brackets because we want to provide some binaries so that you don't have to do all the compilation yourself, because not everybody is going to want to be working at the the coalface and being a project developer for Enarx. Some people want to take it and play with it and see whether they can just get their standard WASM workloads to run, and we want to encourage that, and we don't want you to have to do all the compilation and all that sort of stuff in order to get those. So we absolutely plan to provide example binaries for people to play with. We would love it if you were in a position to audit our designs and our implementations, get involved with documentation, and of course there's always community building and outreach. There was always place for people who are involved, interested in those sorts of things. We spend far too much of our time coding and not enough of our time talking more generally. This is one of the opportunities we have to do that, is this webinar. If you have a particular interest in getting involved on the technical side, here's some of the skills that we're kind of interested in. Nathaniel, why don't you go through these as well?
Yeah, thanks, Mike. So if you already have SEV and SGX expertise, of course, we'd love to hear from you. We are fairly maturing at this point for those technologies, but we would always love more help. And if you have expertise in WebAssembly or you want to get involved with WebAssembly, we do need this. This is probably the roughest area of the project today, and we hope to improve this in the future. But our WebAssembly is, if you have WebAssembly expertise, we'd love to hear from you. If you're interested in low-level systems programming, so microkernels, Syscalls, networking, storage, all of that kind of stuff. I'm about to set my hand to some file system code. So if you are a file system expert, I'd love to hear from you. And if you have Kubernetes or OpenShift integration skills, you've seen from our proof of concept that we are pretty close to having a full end-to-end stack, and we'd love to figure out how to make this work and be deployable via OpenShift. Of course, if you're a security auditor or a researcher, we'd love you to come take a look at our stuff. Tell us how horrible we are. We love criticism, so please bring it. And of course, if you're a good Rustation, we would love to hear from you as well. All of our code is in Rust with a small smattering of assembly. So yeah, we'd love to hear from you.
Yeah, and one thing at the top is most important is a willingness to learn. You don't have to be an expert in all of these. I don't think anyone is an expert in all of these, or even in many of them. But if you want to learn and you want to get in there, I literally learned Rust. I'm part of the project in March, and I'm writing a fairly large wadges of code. So it's a willingness to learn and willingness to get involved that we really like and value in the project. Where can you find us? Well, at any of these places. As I said, these will all be available. We'll make the slides available later on, but it's not difficult to find us. Enarx.dev, Enarx.io redirects there, but we don't use that these days. You can find the code, our chat server. Please join us there. Love to see you there. Twitter and LinkedIn. The YouTube is such a horrible, disgusting URL. I didn't put it in. Just search for Enarx. Licenses Apache 2.0, and everything is written in Rust with a smattering of x86 assembly. And with that, I'm going to open things up to some questions because we want to give you a chance. We've got about nearly 20 minutes for questions. So let me stop sharing and we can answer some questions. I'm assuming we have some questions to go. Right. Hi, folks. What have we got?
Mike, we would ask you the first question for you.
Where should we go? Nathaniel, do you want to have any particular? Here's one from one about what are you using as your WASM runtime inside the enclave? And I guess there's a question then, Nathaniel, about why we chose it. Do you want to start with that one?
Ben, could you read the questions for us?
I can read them out. What are you using as your WASM runtime inside the enclave?
We are using WASM time, and our primary reason for using it is that it is all in Rust, so we get very strong promises about memory safety, and it's fairly performant, which is great, and it's easy to embed. So those are the primary reasons why we're using WASM time.
Cool, that's a good one. There's a couple of more around WASM, so let's do that. Another one, is the WASM program just encrypted or is it also authenticated? What protocol scheme, whatever, do you use for that encryption authentication?
So basically, we have a two-phase attestation process. The first phase, the client talks to the keep manager and asks it to set up a keep. Then the client pivots and connects directly to the keep over an encrypted TLS channel. So this is just standard TLS and HTTPS. And basically, we just have HTTPS endpoints at that point. So it's a pretty simple protocol over HTTPS. Everything, all communications to the keep are encrypted always. Mike, I think you're muted.
I am sorry. Yeah, there's a good follow-up question from that, which is the Enarx runtime involved in the attestation protocol or only the host agent? Do you want to talk about that, Nathaniel?
So the host agent is completely untrusted. Let me speak more clearly with repo names. So the keep manager component facilitates the setup and life cycle of a keep. It is completely untrusted. It does handle some aspects of attestation where the hardware technology does what we call pre-attestation. So this would be the first two versions of SEV, namely SEV and SEV-ES. Both do pre-attestation, and so the keep manager proxies some packets back and forth. Those are either confidentiality and integrity protected or integrity protected using the attestation protocol provided by AMD. So we conform to that protocol. On the other hand, applications which do post-attestation, meaning that the keep starts up and then can perform attestation of itself. Once that happens, all attestation then occurs over the TLS connection.
And in which case, it is, yes, the runtime is involved. So there's another good question on a slightly different one, which is, I'll have a bit of a go at to start with, which is typical usages of SEV seem to imply that the network stack is inside the TCB, an SEV protected VM. How does Enarx implement networking in light of that? And that's a good question. I think the answer to that is that we don't do a typical usage of SEV.
Yeah,
when
so
people think, let me have a go. You can
go ahead,
Nathaniel. So typically, when you talk about a VM, people think of a VM as a virtual machine run by a hypervisor with an OS and a user space and stack on top of all of that. That's not what we mean by a VM. And a VM, in the basic, very simplest case, is a virtual CPU and a memory page, or a virtual CPU and some memory pages. And that's what we mean by an SEV VM. So we take just that and we implement everything on top of that. So microkernel, syscalls, all those things, those are us. So we are in the position, we can actually implement the syscalls and send that networking calls and other things like storage calls directly down into the OS outside and do any implementation we want in the middle with any intercepts. Going a bit further with that, Nathaniel?
Yeah, we have a single interface that is used to handle all communications between the guest and the host. We call this interface Sallyport. And basically, it implements a syscall layer. And in fact, it's compatible substantially with the Linux syscalls. So what basically happens is when we start up our VM, we have a very tiny microkernel that basically gets that first process set up and running. And whenever that process makes a syscall, we either handle that syscall directly in the microkernel in the case of things like memory allocation, things like that. Or if, for example, they're making a network call, that call is just transparently bounced to the host, decrypting the memory pages along the way. This is why we have, one of the reasons why we encourage the use of WASM loader with keep loader, because WASM loader is what's going to implement our encryption on top of these naked syscalls, and that's what will give you the strong security guarantees. So, but that's how our networking stack is outside, because, for example, if you do a read or a write, we actually bounce that syscall all the way to the host.
Cool. There's so many great questions. I'm not sure we're going to get through all of them. Just a quick one here. I'll answer. What are you using Sibor for? Well, the answer to that is we have quite a lot of network communication where we pushing things like attestation information across the wire, or information. Let's say the Enarx keep manager wants to say, well, here are the types of keep I support, and here's how you would address them and ask those questions. And a lot of that data is binary data rather than ASCII data. And although JSON is very good for ASCII data, it's really not very good, or I suppose more than just ASCII, but text data. It's really not good for binary data. Sibor is designed for exactly those sorts of use cases, and so we're using it quite extensively. It's very easy to encode in and out of Sibor, and honestly, it's made our lives a lot easier since we started using it. Let's have another one. Any ones in particular that you want to answer? Feel free.
Yeah, I see two questions here about Python and the Python scientific stack. This is a great question. There is a project called Pyodide, Pyodide, Pyodide. You can just Google for Python WebAssembly. And basically, this is a project to compile the entire Python interpreter and the entire scientific stack to WebAssembly. They are currently targeting WebAssembly in the browser, but it would not be that much work to make it work inside of Enarx once we have pretty robust WebAssembly support.
But you're quite right. There is quite a big difference between compiled languages and interpreted languages and their support and how they run within WebAssembly runtimes. But there is work going on there. We've got a couple of questions about that. That's good. What's another good one? How do we prevent a workload being sent to the platform that is fake and pretends to be SEG or SEV or SGX? I think what the question is how are we sure that a keep is a real keep running what it should run in, what it should be running, and that it's not a spoofed keep? Really, really important question, and the answer to that is attestation. So all of the platforms we support, SEV and SGX, have an attestation protocol built in to the CPU and firmware model, which allows us to make cryptographic checks for every single time we create a keep, and we do not send, the client will not send a workload until it is absolutely certain that a keep has been fully attested and is a real one and is not a spoofed one.
Yeah, I think it's important to note there that these are hardware specific protocols, right? So SGX and SEV have their own protocols, and Enarx abstracts over that by understanding all of the protocols and wraps it up in a simple deployment mechanism. So, one of the checks we make, for example, is that we validate that cryptographically that the CPU is in fact manufactured by Intel or by AMD for the respective technologies, and that the environment is set up, by the firmware of that CPU correctly. So that's really one of the most important things of our project, is that we have to get attestation right in order to to get to the next level. And attestation is really, really hard. For example, attesting a VM is a traditional VM is very fraught with places that things can go wrong. For example, like if you attest just OVMF and you load grub from the disk, well, how do you know that the grub that you've just loaded from the disk is in fact a valid grub and hasn't been modified by the host? And then in turn, grub is going to load the kernel off the disk. How do you know that that kernel is trusted? These kinds of things they're very difficult problems to solve, and we think we've come up with a fairly elegant solution for how to solve this within our own project.
Here's a couple of quick ones. Could you talk about using why Rust? That's a good question. Why Rust?
Yeah, that's a really easy one, actually. So Rust is probably the most interesting language of our generation, because it defines a new memory model, which gives us very strong guarantees about memory safety. So, for example, you're not going to get, or it's very hard to get, memory corruption. And with memory corruption comes all sorts of vulnerabilities. So this is why we're not writing in C or C++, for example, because it's just too easy to make mistakes that compromise the security of the system. And Rust as a language provides us compiler guarantees about the safety of our memory, which we think is very important.
Okay, here's a quick one. Do you plan support for other platforms like IBM PEF? Absolutely. And Intel TDX? Absolutely. Once they become available, we absolutely plan to be working with those. And we have very good links with all of the teams, in fact, hardware teams and software teams doing that. So here's another one, which I'm going to answer fairly quickly, because it's either a very long question or a very short one. Can you describe some of the difficulties you've run into with attempting to unify attestation models for SEV and SGX? Yes, because they're my day-to-day pain. They are quite extreme, and so one of the questions is, Nathaniel mentioned this pre-attestation versus the post-attestation. How you transfer the information, sufficient information, to the client to make have the correct assurances that attestation has happened and that it's got the right data is really quite tricky. And I'll let you go in a bit deeper. Let's not spend too long, because we could spend the next hour talking about this.
I'll summarize it really quickly. So we have this concept of pre-attestation and post-attestation. And basically what this means is whether or not the keep is able to execute instructions before attestation occurs. So in pre-attestation, you do attestation before the guest has started executing, and in post-attestation, you can do attestation after the guest is executing. In the case of pre-attestation, what we do is we have the tenant generate a key pair and securely deliver that key pair to the keep. Only the keep can decrypt that message. And once it does, it is able to set up a TLS certificate using that key pair. The tenant discards the private key and then validates the certificate on the other end against the known public key that it delivered. And therefore, we can trust that it is, in fact, our keep. In post-attestation, the keep can start running first. And then it can request a measurement of its initial state, for example, along with some additional metadata. And so what we do in this case is we have the keep generate a key pair that never leaves the keep. The public key is then included in the attestation report that goes to the tenant. So the tenant receives this report embedded in the TLS certificate. It can validate everything about that report embedded in the TLS certificate. It validates the public key that's been inserted into that report and confirms that that public key is in fact the public key of the certificate that it's communicating to, and then it trusts that it is a keep. So the end result essentially is that we're validating, we're doing additional types of certificate validation on the TLS certificate so that we always know that the party that we are talking to is a fully attested keep.
Okay, there's some too many questions for us. I'm going to try and do a couple of quick ones. Zygmunt, nice to see Zygmunt. That's a long time. Have you thought about how to integrate with other TEs, e.g. AWS Nitro? This is an easy extension. I've already mentioned PEF and TDX. You have a brief comment on Nathaniel on Nitro or not?
Nitro uses the word enclaves, but they don't mean by enclaves what we mean by enclaves, so it's not a good fit. But yes, in terms of everything else that meets our definition of what a secure enclave or a secure TEE is, yes, we aim to support it. We believe that we have a fairly straightforward way to implement for all future systems at this point. Like I said, we have a running microkernel that needs. It would need a little bit of hardware extension, but it is fairly straightforward.
Yeah. One very quick one. What's the state of network support in Enarx keeps? It'll be coming, but it's not there yet. And one final question, which you're going to have to answer very quickly, Nathaniel. But before I do that, please, if you're interested in carrying on this conversation, join us right now at chat.enarx.dev. Nathaniel and I will both be there in the general channel. Chat.enarx.dev. We'll see you there. Would love to chat. So last very quick question is around Syscalls. How we're using Rust inside SGX and AMD, and how many Syscalls are we managing and how many are we delegating? Very quick answer.
I don't have an exact number to give you, but it generally has to do with TEE competency. So, for example, if you want random data, that's actually not even going into the microkernel at all. We're using the CPU instructions directly for that. If you want memory allocated, for example, that will come from the shim layer. So the syscall goes from the guest static elf to the shim layer and is handled directly there and returned. If you're doing any kind of file I/O, that's handled all the way on the host side. So basically, the file descriptor numbers that you get inside of the keep, not inside of the WASM instance, but inside of the keep static binary, are real file descriptor numbers on the host side. And you can access them directly. So the whole thing is very lightweight, and the biggest pain point there is just that all the pages are encrypted. So anytime you want to do I/O, you have to copy and decrypt the pages. But everyone has that problem. So,
Ben, do you want to bring us home?
Sure. Well, thank you very much for joining us today. This has been great. We got there are a lot of active questions. We always love engagement at any level. A quick mention: if you're not familiar with Rocket Chat, you can use it with a login. You can also use it anonymously if you want. If you have a reason to do that, that is totally fine by us, and that's part of the reason why we chose that as a platform. We're happy to have it. So we hope to have more of these on other projects that are part of the CCC. And please reach out if you have any questions, you have any thoughts, or you want to help us out in any way. Please let us know. We'd love to hear from you. Thank you very much.
Thank
See you at the Rocket Chat. Thank you. Bye-bye.